So let us look at this tool, that is yet another compiler. You have already done assignments using Lex tool, fine. So Lex is used for lexical analysis, and for semantic analysis or parsing you need YACC, fine. So actually basically you need Lex and YACC together. So see, you need to write a .y file. So when you save the file, you need to give this .y extension. Then you, compile this file using YACC. So if you are using Linux, then you need to download YACC. Or if you are using Windows, then you need to download Bison. I hope everyone has downloaded Flex and Bison, or if you are using Linux, then Lex and YACC. Fine. So I again repeat that if you are using Linux, then Lex, you need Lex and YACC. Fine. But if you are using Windows, then we have Flex and Bison. Fine. So you give input a .y file to the YACC, and when you compile this file, we need to use -d option, and that -d option generates this header file also, which this header file, that is .h file, which is generated. So y.tab.h is generated, which you need to include in the Lex file. Fine. And the output is and another file is generated, that is again a .c file. Okay, so when you compile your Lex file using Lex command, what happens is lex.yy.c file is generated. Fine. Similarly, when you compile your .y file using YACC, y.tab.c is generated. Fine. But if you are using Windows and Bison, like in my machine, y.tab.c is not generated. If the program name is my language, or suppose if this is the program, okay, mylang.y, then the files that are generated is mylang.tab.h and mylang.tab.c. Okay, because I am using Bison. Fine. But if you are using this YACC, then it will generate y.tab.c and y.tab.h. Fine. These two files are generated. Then what we do is we include this header file.h file, which is generated from here, in the Lex file. And then when we compile this Lex file, we get a lex.yy.c file. Fine. Then we compile these two C files that are generated together using GCC command, and then we get a output file. Fine. So when we get this output file, then we give the source code as input, and we get a compiled code or a interpreted output. Fine. So we get an intermediate code as output. So whatever you have written in the rules, that output you will get. Fine. Now, as you have seen in Lex, you had three parts in the program. In the same way, the YACC program is also divided into three parts, and these parts are separated by these double percent sign. Okay, so you have first part, then the second part is the production rules. Okay, the grammar that goes here in the second part, and you have the third part, which is the main program, okay, that you write in C. Then in first part, like you have in Lex, we have C declarations enclosed in this percent opening curly bracket and percent closing curly brackets. You also have these C declarations in the YACC file in the first part as well. Then you also have these like percent start, percent token, percent union, and percent type. These also you can use in the first part. Now percent start indicates, like you need to write the grammar in the second part of the YACC file. Okay, so in the grammar you have productions. So the non-terminal, which is the start symbol of the production, you need to indicate using this percent start. Okay, then percent token, here you need to list the tokens that are returned by the lex file. So you need to declare it here in the YACC file. Then percent union, this is, you can consider this is same as union that you have studied in C. Okay, so I think till now you have not come across any application where union is used, right? We saw that we have union in which memory is shared between the members of the union. But here, when you declare different data types in the union, these data types are the data types of the tokens or of the non-terminals. Okay, so it shows that which non-terminal is of which type, or the value that non-terminal holds is of which type. Fine. So this union is the union that you have seen in the C language. Then this type represents the type, which the data type. Fine, that we'll see in the example. I'll let you know about all these in details. When you see the example, you'll understand. Fine. So this is the first part of the YACC file. Then in the second part, that is the middle section, you need to write the grammar, which is basically context-free grammar. Fine. And if you have multiple productions for the same non-terminal, then you can separate it by this pipe. And every production is terminated by a semicolon. Fine. Then, as we have seen, the syntax directed translation scheme in the theory class, what we do is, in front of every production we write the code. Fine. Likewise, here also in front of every production you need to write the C code, that when this production is reduced, what you need to do, that you need to write. Okay, so actions associated with a rule are entered in braces. Fine. Then let us look at the example. So suppose this is the grammar. So this statements, this is a non-terminal. Fine. Then this statement is another non-terminal. So the grammar, this arrow, instead of arrow, you need to write colon here. Fine. So statements, colon, statement. Fine. So this is one production. And in curly bracket, you are writing the action. Okay, semantic action, what you need to do. So in semantic action, we have just written printf statement. Fine. Then this is another production. So you can see pipe is used here. So statements, arrow, you have statement, space, statements. If you have this production, when this production is reduced, this is the action that needs to be performed. Fine. So this is how you need to write grammar in the middle part or the second part of the YACC program. Then in the productions, these $1, $2 till $n can be referred to the values associated with the symbols. Fine. So suppose here I want to print the value of statement or the value that the statement holds, then I need to use $1. Okay. So this part, this side of the production, that is left side of the production, the non-terminal, we referred it by double dollar. Okay, dollar. And this part, right hand side of the production, every symbol is referred as $1, then the second symbol as $2, then third symbol as $3, and so on. Fine. So these are associated with the symbols, and this double dollar refers to the value of the left side of the production. Fine. Every symbol have a value associated with it. Fine. And default action is $1 is equal to $1. This is the default action if you don't write any action. So see, if you have a grammar production like statement colon identifier plus identifier, then this statement non-terminal, we need to refer it as $. So the value that this statement holds is this $. Okay, you can consider this as an attribute of the grammar. Okay, so every grammar symbol Okay, non-terminal, it has attributes where we store the values, right, that we have seen in the theory class. So the value that this non-terminal holds basically is represented by this double dollar, because this non-terminal is at the left hand side, and this right hand side you can see what is written here. Double dollar is equal to $1 plus $3. Okay, so $1 represents this identifier. So this is referred to as $1. Then this plus is referred to as $2. And then this identifier is referred to as $3. Okay. So what we want to do is we want to add these two values. So that is why we have written $1 plus $3. Fine. Similarly, for this next production, statement arrow identifier minus identifier, for that the semantic action that I want is double dollar is equal to $1 minus $3. Fine. Now let us look at the third part of the YACC program. I hope this say another 12th slide is visible. Yes, the third part of the YACC program. So it contains the C code, okay? The C code that you want to write, or any functions that you want to write, the main program that goes inside this third part of the program. Fine. So now let us look at the program. So see, this is a 2.l file. Okay, this is a L file, that is a lex file, which in which this first part, you can see in this first part I have just written declarations. So this is hash include stdlib.h. Then we have YY This is a function that I have declared here. And you can also see that I have included 2.tab.h. Why? Because I have a 2.y file. Fine. So the name of the file is 2. Fine. So I have two files, that is 2.l and 2.y. So this 2.y, when it will compile, it will generate a header file also, which is 2.tab.h. Fine. As I told you that since I'm using Bison, it is not generating y.tab.h. It is generating, it is giving the name of the file. So 2.tab.h is the file that I need to include here in the lex file. In this declaration part, I need to write. Fine. Now in the second part, you might have understood what is written because you already know how to write programs in lex. So this recognizes all the integers. Fine. So 0 to 9 plus. What we are doing is we are converting this YY text because it is of type character or string. So we are converting this to integer and we are returning a token that is integer. Fine. Then if you have minus, plus or slash n, then you are returning that value. Fine. Then for space and tab, you're not doing anything. For brackets also, you're not doing anything. And for other than these symbols, if anything else appear in the input, then you call this YY function by passing this string, that is invalid character. Fine. Now this is a YY function that is defined here. Then let us look at 2.y5. So here you can see in the first part, here this is the declaration part. So hash include stdio.h is written. Then int yylex function is declared and YY function is declared. Fine. Now you can see in this, from this 2.l file, we had returned one token which is integer. Fine. I hope when I'm switching the screen from 2.y to 2.l, it is visible. So yes, so you have one token that is returned from .l file. So that is why I need to declare that token here with this percent token, and we need to declare this integer. Fine. Now this is the grammar. So program, this is the non-terminal. Okay. So program arrow colon, we have program expr slash n. Fine. And see what we need to do. We need to print what we are printing. We are printing this expression expr. So this is denoted by $2. Fine. So $2 we are printing. Okay. Then this expr is also a non-terminal. So we have a production for that, that is expr arrow integer. So we have an action which is $. So $. Represents the value of this expr. So $. is equal to $1. Then if we have this expr arrow expr plus expr, for these productions you have this semantic action. Fine. Now, in main, you are just calling the parser. Fine. Now, let us execute this. So, first I will compile the .y file using this Bison. So, Bison minus D, because I want the header file also. So, minus D and 2.y. Fine. So see, it is compiled. Only this is the warning that this grammar has some conflicts. Okay. Shift reduce conflicts are there. Why? Because when you compile, the table is generated. Okay. Parsing table. Then I will use flex 2.l to compile this lex file. Fine. Then you need to use GCC. Now, when you have compiled this .y file, we have got 2.tab.c. Fine. So, we need to write GCC, then, and we also have lex.yy.c file from this 2.l. Then we have 2.tab.c file, and I want the output in suppose a file named as 2. Fine. So now these two files are also C files are compiled. Now to execute, I'll just give 2. Okay. And I need to give an expression, an integer. So you can see what is accepted in this program. This program is accepting only integers. Wait, I'll show you the .l file. So see, for 0 to 9, for integers only we have these definitions for plus, minus and integers. For anything else, you are returning invalid character. Fine. So here, if I say 2 plus 3, then it is giving me the output 5, right? Suppose if I say 8 minus 2, it will give me an output. But if I give something else, say a is equal to 5, then it is saying invalid character 2 times. Why? Because a is an invalid character. So for a, it is returning this invalid character. Then for this equal to also, it is returning invalid character. And this 5 is printed as it is. Clear? So I hope you have understood this program. Okay, so this was a very simple program which is used only for plus and minus. Okay, so let us look at another example. So this is another example that I've brought for you. So this is again a .y file. First, let us look at .l file. So we have cal.l. Here what we are doing is we are, if I get a string print, then a token named as print is returned. If I get a string as exit, then a token named as exit command is returned. If I get any character, okay, a single character, because here we don't have any plus. Fine. So if you have a single character between from small a to small z or capital A to capital Z, then what we are doing is we are returning this yy val.id. Now what is this id and what is this num? Okay, for this let us go to cal.y. So first let me explain you this. So you can see here what we have done in the declaration part. We have declared this YY function. Then we have declared these two library files, that is stdio.h and stdlib.h. Then we have these two functions, that is symbol value and update symbol value functions. And we have a integer array, that is symbols of 52. Basically this is acting as a symbol table. Okay, symbols array which will hold the value of the character. Okay, so a b c d user can enter, though these are the identifiers. Okay, so but the variables, we have restricted the name of the variable to be of only single character. Fine. And that is why for from small a to small z and capital A to capital Z, total we have 52 characters. Okay, 26 plus 26, we have 52. So that is why this array is declared of size 52. This symbol value takes a character as input, and this function is used to store the value of that symbol in this symbol table. Fine. And then we have another function, that is update symbol value, which takes the symbol and the value and it updates. That means it stores this value for this symbol in this table. Okay, so the zeroth index of this symbol represents small a, the index 1 represents small b, and so on till index 25. So 25 index represents small z, then 26 represents capital A. Okay, so that is why we don't have a two-dimensional array here for storing the character as well as its value. I hope you are understanding. We are not storing the name of the character. We are assuming that we have these 52 characters, and the zeroth location, zeroth index of this array is for small a, then one index is for small b, and so on. And then capital A is starting from 26 index, and then 51 index 51 is for capital Z. Fine. And we are storing only the values for those variables, that is the characters here in this symbol array. Fine. So this update symbol value will store this value in this symbols array. Fine. Now when you look here again, we have these you can see percent union. In this we have declared two data types, two variables, you can say. One is of integer, which is this num, and other is of character, that is id. Fine. So in this .l file, this num and id comes from this .y file. Okay, so we have declared two variables here. Fine. Then we have grammar. So the start symbol of the grammar is this line. Okay, and that is why this person start indicates that this line is a non-terminal, which is the start symbol. Fine. Then we have various tokens. So you can see from the .l file, we are returning this print, we are returning this exit command. Okay, so these are the tokens. So this print and exit command, these tokens are declared here. Fine. Now from the .l file, we are also returning integer and number. Okay, so but this integer represents this id. Okay, this id holds this value yy text zeroth value that we are returning. So it will hold this value, and we are referring to with this token, that is identifier. Fine. Similarly, this number is returned, but we are referring to that num as a number token. Fine. So you need to specify here that percent token, this number is of type num. Fine. This identifier is id. Fine. Then we are also assigning type to various non-terminals of the grammar. So the non-terminals of the grammar are line, exp, term, and assignment. These are the 4 non-terminals, and we are assigning type to these non-terminals. So line, exp, and term, these are of num type, that is integer. You can see here num is of integer type, and this assignment is of character type, that is id. Fine. Now, when you look at the grammar, so if you have line arrow assignment semicolon, so whatever I will give as input, the every statement should be followed by a semicolon here. Okay. So assignment, then assignment is what? An identifier. Okay. Equal to exp. So what we are doing is, if we get such type of assignment statement, then what we are doing is we are updating the value. We are saying percent $1 comma $3. $1 means this identifier. This identifier is what? This YY this ID which we have passed. So whenever we have a character, okay, in the input file, we are returning that character and we are passing it to this function. Okay, so what this function will do, we have written the definition of the function here that I'll explain you. But when you have this type of statement, that identify equal to expression, this function is called. Fine. Then you have another production, that is line arrow exit command. So if I type exit, okay, so see, if I type exit, what is return from the l.l file? Exit command token. Okay, so when I get this token, that means I need to call an exit function, so I need to stop. Fine. Then if I I write print, if I have a print string that is there in the input, then this .l file returns print. And here you can see, if I have print expr, then what I'm doing is I'm calling printf statement, which prints printing and the value of this expr. So expr is denoted by $2. Okay, this print is $1. We want the value of exp, which is $2. Fine. So these are the actions that I need to perform. I can have recursion. That is why we have line arrow line assignment, line arrow line exit statement, line arrow line print expression. So these are same. Okay. Instead of $2, $3 is written here because this expr is in the third position from here. Fine. Now, when I get an expression like this, exp, arrow exp plus term, then I need to do these calculations. Okay. So I've written it like this. If I have simple an identifier, okay, I need to just give that identifier a value. So I'm just calling this symbol value function. Fine. Now see, this is the third part. What we are doing is, in main, we are just, initializing the array with all zeros first. Okay. And then we are calling this YY parser. Okay. We are calling the parser. And what it will do is, it will parse the string using this grammar. And then it will call these respective functions that you have written here. So let us look at these functions. The first function is this compute symbol index. So what this function does is, it takes a character as an argument and it checks whether that character is a lowercase character or a uppercase character. Fine. And then it returns the index of that character. As I told you that we are assuming that the array with the zeroth index of the array represents small a, then index 1 represents small b, and so on. So depending on which character is passed to this function, it returns the index. Fine. So it calculates the index like this. So if it is a lowercase letter, then the index will be equal to this letter minus small a plus 26. Fine. And if it is an uppercase, then we have index is equal to token minus a. Fine. So this function returns the index. Then this symbol val, this function simply it calculates, it calls this compute symbol index, it calculates the index, and it just returns this value. Okay, it returns the value of that symbol. Fine. And then this update symbol, this updates the value. Clear? So you can see symbol, and we are using this index, and this value goes here. And here this function, this returns the value. Fine. Now let us execute this program. So first I will write Python, then cal -d cal dot y. Fine. So then I'll say flex cal dot l. These two files, you might have seen that in the previous program also I had given same name to .l and .y file, but it is not necessary. Okay, you can have two different names for these .l and .y files, but for my understanding, or when the programs are saved, I should know that the .l and .y file, this is the .l file for this .y file, and that is why I am using the same name. Okay, because after few days or few weeks when I'll refer to this program, I need to go through the program to understand which is this program, and which is the .l file for this .y file. So if the names are same, then it will be helpful for me, and that is why I'm giving the same name. But it is not compulsory. You can use different names for these two different files. Okay, so flex I have done, then gcc, then I will write lex dot yy dot c. Then for this dot c file that is generated from by Bison is cal dot tab dot c, and I want the output in this calc file, output file. Fine. So these are the warnings. So let us not look at it. There are no errors. Then for execution, I'll write calc. So we can give input as a is equal to 5 plus 3. Okay. Then if I want to print the value, I'll say print a. So see, it is, oh, I'm not giving semicolon. Wait. Every statement should be followed by a semicolon here. So this is 5 plus 6, suppose, and semicolon. Then if I want to print the value of a, then I'll say print a semicolon. So see, it is saying printing 11. So I hope you are understanding. See, what I have entered, a is equal to 5 plus 6 semicolon. So this .l file, it reads the input. So this a, it will return this a, okay, as this identifier. Then equal to is returned as it is from here. Then 5 is returned from here. Okay. Then plus again as it is. Then again the value of 5. Okay. Then we are saying print a. So print returns a token print, and a is returned from here. Now what this parser does is, when it parses the string which is this a is equal to 5 plus 6 semicolon. So it is this assignment operator. So you have an identifier. Yes, this identifier was first returned. Okay. So this identifier is equal to expression. So it updates this array, and it stores the value of this a. Okay. It calculates first 5 plus 3, and it stores the value of a, not 5 plus 3, 5 plus 6, and it stores the value of a in this symbol table. That is the array that we have declared. Okay, it calls this function and it stores. Then when we say print, then using this expression, this production, it prints this value, and it prints printing 11. Fine. So this is done. Then suppose if I say b is equal to a plus 5. Okay, semicolon, and let us print the value of p. See, it is 16. So the value of A, it has taken from the array, okay, because this is an identifier. So this symbol val is called, and this will return the value of this A. It will add it to 5 and it will store in the array where indicated by this B, okay. And when I say exit, then and semicolon, then it exits. Fine. So these were the two programs to explain you how YACC works. So Lex and YACC together, you can write semantic rules. These were very simple programs just for calculating plus and minus. Only the difference was that here in this program, we just didn't use any characters or assignments. We just, we wanted as input like 2 plus 3, 2 minus 5, like, simple calculator which calculates plus and minus. But in this program, we are accepting assignment also. We are storing the value of the characters also. So we are accepting variables which are of a single character. Okay.